What's up, everyone? Welcome back to the second episode of my series about light. Today we're going to be talking about the wave-particle duality of light. It all started in the late 1600s, where Newton proposed that light is made up of particles. However, at the same time, a Dutch physicist named Huygens proposed that light is actually made up of waves. This was debated for many years until Thomas Young finally performed the Double Slit experiment in 1801. Young placed a card with two slits in the sunlight and observed its shadow on cards at various distances behind it, and also against the wall. If light behaved like a wave, like a particle, as Newton predicted, you would expect to see two bright lines on the back card. However, this is not what Young observed. He saw many lines of varying brightness, with the brightest lines at the center, and they were getting dimmer towards the sides. By doing this, he had proved that light behaved like a wave. Now, to explain why Young saw many lines, I'm going to demonstrate how water waves interfere with each other. So when I generate waves with one source, you can see how they propagate outwards in this circular pattern. Now, when I add a second source, things start to get weird. The waves from the two sources start to interfere with each other. And you can see when peaks meet peaks, we get an extra tall wave. And when troughs meet troughs, an extra low wave. They add together. When peaks meet troughs, they just cancel out and there's no wave at all. So this is why Young saw many different lines. The light coming through each slit was interfering with each other. So this should have settled it, right? Light is a wave. Well, not exactly. Over 100 years later, in 1905, Einstein first demonstrated what's known as the photoelectric effect. He discovered that light with enough energy could actually eject electrons from the surface of a material. You see, negatively charged electrons are attracted to the nucleus of the atom due to the positive charge. And if you want to remove an electron from its atom, you have to provide it with at least a certain binding energy. So photons with a minimum binding energy could actually remove electrons from their atoms. And the energy of the photons corresponded to the frequency of light. More about that in a later video. So no matter how intense the light was, if it didn't have a certain frequency, it wouldn't eject any electrons, proving that light is a particle, one photon for one electron. To demonstrate the photoelectric effect, we can use an electroscope, which measures charge. So this part, from the plate to this needle, and this rod and this needle, are all metal and all connected to each other. So any charge placed on the top will be transferred down into the rod and the needle, and they will repel each other, like this. So when it's neutralized, the rod comes back to the position here, and you won't see any deflection. So back when the electroscope is negatively charged, we can shine a light from our little flashlight over here onto the plate. And what Einstein found is that visible light, such as red light here, would have no effect on this electroscope. However, light with a higher energy, such as UV light, would be able to actually discharge the electroscope. We're taking away these electrons by ejecting them off the surface and bringing it back to its state here. Alright, well, after all that, what actually is light? Is it a particle? Is it a wave? Neither? Both? Well, the answer to that question is that the quantum world is weird, and light can actually act as both a particle and a wave. The way I like to think about it is that light travels as a wave until we actually measure it, and then it has a definite position. And the wave function tells us about the probability that we will find the particle in any given location. This explains why in the double slit experiment, light interfered like a wave until it hit the card, where each photon was only in one place. The YouTube channel Minute Physics also gave a really good analogy where light is like a small particle in like a droplet of water. As the droplet spreads out or splits into multiple droplets, the probability that you'll find the one particle in any one spot corresponds to the size of the droplet in that location. So if it splits in two and you have one big droplet and one small droplet, there's a higher chance you're going to find the particle in the area with the big droplet than the small droplet. So that's all for this video. Thanks for watching, and don't forget to subscribe so you won't miss the next video in this series.